welcome back. Our next speaker is Ernesto Mordecki, and the title is Dynkin Games for Lévy Processes. Ernesto, please.
Okay. As I was saying, I wanted to say thanks to Goran, to David, to the organizers in general for this very nice conference in this fantastic institute, in this fantastic place. So I'm going to talk about Dynkin games for Lévy process. Lévy process is one of my beloved topics, and to put the talk in a general framework, I think there are many interesting problems that can be solved or considered that have instances that have been solved, and there are many open problems for Lévy process. Of course, for diffusions also, but today I'm going to talk to concentrate in Lévy process. In particular, in the two blue problems, the optimal stopping problem that gives names to this conference, and the Dynkin game that are related. Okay, so to make notation clear to everyone, we call a Lévy process a process that departs from zero and has independent and stationary increments, and has also a Cadillac path. Okay, so it is a definition of Brownian motion, but we drop the continuity, so to say, no continuity, so we can have jumps. It is interesting. This is what it is said here, that when I wrote my PhD, the name Lévy process was not yet used, and the name was process with independent and identically distributed and stationary increments, as it is called in the classical book by Jacob Chirac. Okay, so to characterize, to know the law of a Lévy process, we have this tool, this analytic tool, that is the characteristic exponent that describes the characteristic function. And I prefer this notation because you know that there are several notations with i's and minus and different, but I prefer this notation. This is the shortest one, the most economic one, the one that saves you to writing minus signs and so on. But all good things have to pay something. You should think that Z belongs to the imaginary axis. Okay, so here we have a drift, we have a variance of the Gaussian part, and we have a jump measure. Okay, so this is the Lévy-Khinchin formula. We're going to go back to this formula. And the main ingredients of my talk are the supremum and the infimum of the process in a stochastic interval. And the interval ends in an independent exponential random variable with parameter R. R is a parameter, but it also plays the role of the discount in financial contracts. It's the same R. Okay, when we are able to solve a problem in this context, this R is that R. Okay, and the tool to determine the law of these two random variables is the Wiener-Hoff-Rogozin, I would say, factorization, because Wiener-Hoff was for random walks and Rogozin wrote the paper for Lévy processes. And this identity has the nice property. So this is known. Okay, this is data of the problem. This is related to your process. If you are able to obtain a factorization in such a way that this factorization involves two characteristic functions, one, it is well behaved when Z is negative because this is positive, and the other that is well behaved when Z is positive because this is negative. So you have convergence. So if you obtain a factorization, then this is the true factorization because this theorem has uniqueness. Okay, we are going to rely on this fact. And in order to factorize, I will advance a little. One looks at the poles of this equation, meaning one looks at the roots of this equation when one thinks that Z now is a complex number, okay, or even a real number, because we began in the imaginary axis, but now we pass to the real axis, okay? So this will play a role in what follows. So I want to pay attention to three particular models. The results I am going to talk are for general Lévy process, but I will have examples on these three particular models. One is very simple, that is Brownian motion with drift. And here is the characteristic exponent. We have no integral part because there are no jumps. The second one is a process used in actuarial mathematics, the well-known Kramer-Lumber process. So it is a positive drift minus jumps, and the jumps have exponential distribution. This is, you can read this here. This is a jump measure, and you obtain, after some computations, the characteristic exponent. And the third one is the double exponential compound Poisson process. So you have positive exponential jumps and negative exponential jumps. Okay, so these are three models, three classical models, I would say. And here is now the measure has two components, positive jumps, negative jumps, and the characteristic exponent has this shape. Okay, so we proceed in one example to show how to compute the distribution of the supremum and the infimum. So to say how to use this Wiener-Hopf formula. So we have this expression, okay, this function R minus C of Z, that is the denominator. And this equation has two roots. Okay, here is the plot. Now I consider Z to be a real number. And I have these two roots that are indicated there by hand, okay? These two roots, because this is the function psi that has two poles, 1 and minus 1 with the chosen parameters, and I have these two roots. So what do I do with these roots? I simply factorize. Okay, this is, here you have after some computations, you have simply a second order equation, you find the roots, you factorize like in high school. And you use this theorem of factorization of residual, of rational functions, and we come to this expression. So the first factor is the characteristic function of a negative random variable, okay? And the second function is the second factor is the characteristic function of a positive random variable. So by uniqueness, these are the characteristic functions of the supremum and the infimum, okay? So this is simple application. And it happens that they are defective exponential distributions, okay? They are defective because of this term R1 over alpha and R2 over beta that do not have Z. So when you go back with the Laplace transform, with the Fourier transform, you get a Dirac delta, okay? So these are known results. I mean, this is not new, but it's very nice to do it so simple. I mean, to find the distribution of these objects. And the same happens with models 1 and 2. Okay, I show the third one because it is the more involved. But for Brownian motion, this is direct. This is in Bertrand book or in many places. And the Kramer-Lumber is similar. But it's interesting that here we have one atomic distribution for the infimum, but the supremum has a proper exponential distribution. Okay, and this was the third one. So finally, and this is a new fact, I consider one general model that includes the three models. So to say, put in a pi and 1 minus pi, and I have this characteristic. This pi can be 0, both. So I get the Brownian motion. One can be 0 and the other not. So I get the Kramer-Lumber, or both can be positive. Then I get the double exponential. So I like this very much because the models in principle are very different. Because you have Brownian motion on one side, you have double compound exponential. So, but this approach allows for a unified treatment, analytical treatment of the three examples. Okay. So this was the previous part on Lévy process. Now we are going to talk about some results in optimal stopping. So this is our formulation of optimal stopping. In particular, we have perpetual problems. We have a strictly positive cost. We can do with R equal to 0, but the process has to be transient. And okay, there are some particularities that I do not want to enter now. So the problem is to find, as you know, the value of the game and the optimal stopping rule, okay? So in order to do this, we wrote a verification theorem. What is a verification theorem? Is a recipe to solve the problem. So the recipe has ingredients. So you have to find your ingredients. And if you find your ingredients, the theorem tells you how to obtain the solution. So what are the ingredients? The ingredients are two functions. One function is, the Q sub star is related to the infimum, and the Q superstar is related to the maximum. So you have to find these two functions that in the literature we call them averaging functions in such a way that you can reconstruct the function G, okay? And you reconstruct the function G not for all the values, but for the stopping set of the problem, okay? So if you are able to do this, and if now you give freedom to the X to move in the whole X, and you obtain a function that is larger, then this function is the solution, okay? So this is an extension of the classical result of the one-sided problem with the supremum, okay? This has a supremum and a maximum, and it is interesting because Soren with Pavo and Baug wrote a paper where here we had an infimum, okay? So it is a related paper, but it's not the situation. And okay, and we also had a paper with a sum with Salminen 2006. And finally, this is a little more explicit, but this is a solution. Okay, so the problem, of course, you say, okay, what are these functions? Okay, how to find them? And it happens that the border of the interval, this X sub star and X superstar are define the optimal stopping set. So the drawing here is like this. Here you have, here I have X, and here I have a function Q, and here I have a function Q. So this is more or less the drawing of the functions that we have to find. So if you have the functions, then you find the roots, and the roots define your stopping set. So this is a result published some years ago with a master's. At that time, Facundo Liu was a master's student. Now he has obtained his PhD in Uruguay and in related problems. But okay, so we are going to show an example. One of the three cases, so I choose the double exponential compound process, the third process, but all the examples can be done. And the payoff function is absolute value of G. And in this case, we are able to find the functions and the optimal levels, and we obtain an explicit form for the value function B. Okay? And we show a numerical instance of the solution. So in fact, here we have the function G, the absolute value, and here we have the stopping levels, and here we have the function B. Okay, so this is the structure of the solution. Okay, it is okay, you can say how to find this. I will say a word how to find these functions. What we do is here, as we know, the densities of this or the distribution of these are unknowns. So we get some integral equations, okay? A pair of integral equations, one on one side, one on the other side, and we manage there, and we finally came to the functions Q. Okay. So this is, sorry, oh, I was going back. This is the optimal stopping case. Then this is a numerical example. We have no smooth fitting at any of the contact points. And of course, if we have Brownian motion, we get smooth fitting at both points. And if we have compound Poisson, this Kramer-Lumberg, we get smooth fitting only at one point. But we do not use the smooth fitting to solve the problem because we do not have it. Okay, so this is optimal stopping. So now we come into the Dynkin games part. Okay, so this is in principle a completely different problem, because instead of having one player, we have two players. Okay, it's like putting in an optimal stopping problem the option, giving the option of the issuer of the contract to decide also the moment to execute. And as he will have to pay, the holder will try to maximize, but the issuer will try to minimize. Okay, so this is in financial terms more or less how it works. Okay, so we have two payoffs, G1 and G2, and each player chooses a stopping time, and the player min has to pay to player max this amount of money, okay? Where G1 in my talk is smaller or equal than G2. You can think that G2 is G1 plus a penalty, okay? So I am giving a contract, so paying a penalty, I am the issuer of the contract, and I can choose the execution time paying a penalty, okay? So it is really a game, okay? It is not clear, depending on the penalty, whether it is convenient for me or not, whether to execute or to wait the holder of the contract to execute, okay? Sorry. So this is the Dynkin game. So as always, we are the bank, we are not the player. So we have many contracts. So we want to maximize or minimize in expectation, okay? And we define these expectations. So we define this function that depends on the initial point on both stopping times. And max player tries to maximize and min player tries to minimize, okay? So the general solution of a Dynkin game is, there are many contributions, but this paper by Goran and Erik Ekstrom gives I would say, for my purpose, a complete solution of the problem, because it characterizes the existence, it gives the form of the stopping sets that are entry times to these sets, and if the process has good properties in the path, like our Lévy processes, then we have an equilibrium, so to say, in a very general framework. Okay, this is a very nice paper with more than 100 formulas. Remember as well. Okay, so now we go into the Lévy process case. We are going to use this formula. I'm going to present some results that are submitted. And we consider a general Lévy process. We consider a positive discount. And we ask this function GI not to grow too fast, and the speedness of growth is related to the process because this alpha is the same parameter. So we should find some conditions on the growth of the function, okay? And we have a verification result. And the verification result is similar to the previous one, but for a very different problem. So this is interesting. So we have a Lévy process, we have two continuous reward functions. We assume that there exist 2 points. Now the notation has changed a little, xi and xs. And we need to find two averaging functions. But the averaging functions in this case are different, of course, because the problem is different. One has this shape, and the other has this shape. So to say, they are both increasing, but one is positive and the other should be negative, okay? So this is the difference. And they should satisfy this condition. So to say, in one half line, there should be equal to one function, and in the other half line, there should be equal to the other function. Remember that G1 is smaller than G2. And as in the previous case, if we construct the function v and the function v satisfies this good property, that is a property of the solution, then under the sole condition, this is the solution to the problem, okay? So we find, in a very different problem, we find a similar application, okay? This is, I found this nice, I mean. Okay, so what to do with these examples? Okay, one word about the proofs. The proof of this type of results rely heavily on the strong Markov property of Lévy processes that give what is called fluctuation identities. There are in the book by Andreas Cipriano, it is explained in detail, and there are many optimal stopping problems solved there. And okay, we obtain that in the continuation set, that it is between these two lines. Okay, I will write here my Dynkin game case. So here I have the Q plus star. Here I have the Q and the star. So this is XS, this is XI. So this is the continuation set, where neither of the players stop. So they say they both wait. So the sub player waits for the process to come to this set and stops there, and the if player waits for the process to come here and stops there. Okay, so this is the structure of the solution. So the process here is harmonic, so to say, and if we got here one property and the other property, okay, these are I wouldn't say simple computations, but we more or less know how to handle and how to prove this. This is not long proofs. Okay. And here there is a comparison between both problems, the optimal stopping problem and the Dynkin game. And it is interesting that the value function has formal the same structure, but this function has the same shape, but this is positive and decreasing in the stopping problem, and negative and increasing in the Dynkin game, okay? So there is an interesting conclusion here, because if we compose a decreasing function with the infimum, we get an excessive function. So in the optimal stopping case, we are summing and obtaining an excessive function. This is known, of course. But in the Dynkin game, there is a novelty, because it happens that the value function is the difference of two excessive functions, okay? One related to one player and the other related to the other. And this is still discussed in the literature, how to characterize, okay? We all want to obtain the Dynkin theorem for Dynkin games, so to say. The Dynkin theorem that the value function is the least excessive measurement and so on. So there are many attempts to do this in the literature, and this is, okay, this was not the purpose of our theorem. We wanted to solve a problem, but this is a consequence of our theorem when we observe the form of the solution. The solution is the difference of two excessive functions. Okay? So, there is also a corollary on smooth pasting, and we need the properties of this function Q. So this is stated in general form. So if for functions of this form here, okay, under some regularity conditions, if Q is C2, then we have an atom of this size if the supremum has an atom. Okay, sorry, I said wrong. We have a difference in derivatives. Okay, we have an angle of this size if the supremum has an atom, and in all the other points, we have we have differentiability, so to say. So we can apply this because this is our solution is the sum of two of these things. So we apply this theorem and we know whether there is a smooth fitting or not. Okay, how to use this theorem? As I mentioned, this is the departing equation here. So here we get some integral equation that after some manipulation becomes an ordinary differential equation in the examples when we know the distribution of the infimum and the supremum. And we found the points conditioning on this inequality. Okay, so here are, this is the end of the talk. We have 3 examples. So this is for the Wiener process with drift and without drift. Sorry that it is with drift, but here there is no drift. And the functions are x minus 1 and x plus 1, okay? So and this is with drift. I am very fond of this example because it is a symmetric example between the if player and the sub player. If you put a minus sign, then all reverts and it's symmetrical, okay? And up to my knowledge, and I would like to know if somebody of you know, this example was not considered in the literature, up to my knowledge, okay? Because known examples require the functions to be bounded from below, so to say. Up to my knowledge, I repeat. Okay, so we have smooth passing here. We have, okay, this is what I mentioned. Our purpose was to provide the simplest possible example, okay? Because it is very good to have a simple example, because when you produce a method, you should try, you should have examples to try. It is necessary to develop the theory. Okay, so I see it similar as the famous Taylor's example, 68, one of the first examples in optimal solving. But this is my view, of course. But here, in particular, we can observe that when the discount goes to 0, the contact points here go to plus infinity, plus and minus infinity, okay? Because you have no discount. And finally, when R is equal to infinity, you have no solution, and it happens that the conditions of the theorem are not verified. So it is important to solve these examples to have R strictly positive, okay? Okay, so here on the second example, we have two pictures. The first picture is the characteristic exponent. Okay, so we draw in dashed line the level R, and we have these two roots. With two roots, we construct the distribution of the infimum and the supremum, and we find the solution solving these ordinary differential equations. Okay, and the solution is written here. And there you observe that you have smooth fitting here because the supremum has no atom, but here we do not have due to the fact that the infimum has an atom. Okay, so this is very simple. And our third example is similar. And we have two set of values. We have a symmetric situation, okay, where alpha, beta, mu, nu are the same. So the upper jumps are equal to the lower jumps. So we have these levels. Sorry, this should be xi and xs, because this is the Dynkin game, but this value. And in the right, we have another instance where the solution is written like that, and we have no smooth fitting at any of the points. Okay, so this is my time. This is the last transparent. I have, okay, a discussion on possible extensions. Okay, you can say and probably ask, okay, but what happens if you are not able to find the characteristic function, sorry, the densities of the infimum and supremum? And here I have a hope, but no results, that I can, so to say, pass to the frequency domain this equation, where I can find the characteristic exponent of supremum and infimum, but not the density, and work there. Okay, but this is a hope. This is not so. And hopefully also we can solve more involved examples. Okay, and my last diapo is to announce, sorry to use the space, but our Latin American Congress in Probability and Mathematical Statistics in these dates. If you want to attend, if you want to know our city, we will have a small session in optimal stopping, so you write, and that's it. Okay, thank you for your attention. Thank you very much.